Hi, everybody.
Hello.
So, let's give everyone a few minutes to, other people a few minutes to get here. All right. Does anyone have any questions about anything to start? Okay. All right.
Are we gonna recap what we did yesterday? But other than that, I don't have any questions.
Yeah. I'll very briefly just recap what we did. Um, and then let me know if something comes up when I'm doing that. So I was just gonna say one or two sentences about what we did last time. So last time, oops, I should share my screen. Okay, here we go. So last time, we defined the Cesaro sums, the Cesaro means of a function, Cesaro Fourier means of a function. So given, say, f, a continuous function on the circle, we said sigma n of f of x was defined to be 1 over n, the sum from n equals 0 to n minus 1 of Sn of f, where Sn of f is the partial Fourier, the partial Fourier sums. So the sum n then f hat n e to the I n x. These are called the Cesaro means. Of f. And the main result that we proved, so we showed that f, a continuous function on the circle, implies that you have uniform convergence of the Cesaro means of f back to f as n goes to infinity. So that these, so in other words, these functions give a nice approximation of the continuous function f. These partial sums, these Cesaro sums, partial sums, in the sense that as you let n be large, as you let n go to infinity, these converge back to f again. So for any fixed large n, this function, which is a trigonometric polynomial, is kind of arbitrarily close to f in the supremum norm. And we deduced a bunch of consequences from this. Namely, we showed that the trig polynomials are dense amongst the continuous functions because each of these is a trig polynomial. We recovered the result from that we proved that we worked very hard to prove a couple of lectures ago, namely that if you know a little bit more about the function f, namely if you know it's C alpha, then you in fact have uniform convergence of the partial Fourier sums back to f. And we used this theorem as a this theorem right here as a key tool in that proof. Okay, so and we started discussing it. We discussed it. We motivated this a bit. We discussed a bit what's going on here. But I want to do that. I want to discuss a little bit more because I want to introduce yet another means of summation as well. Is that a good recap? Good enough recap for us about last time? Is this what you were looking for?
Yeah, I also had one other thought. I guess it's not a question, but
Yeah.
So you wrote like sigma n in terms of Sn, right? Basically,
Yep.
as like the averages, but then
Yep.
you could like go backwards and say like Sn like n plus 1 sigma n minus n sigma n or something like that. So then is that useful at all?
So,
I don't know if that makes sense.
let me just make sure I understood. You wanted to say that that S. So you want to rewrite S capital N, say in terms of these sigma n's.
Yeah.
So what do we get here? We would get S capital N of F n times this maybe I guess. Oh, sorry, is equal to um, n times. I'm going to mess up the algebra, but I see what you. I'm going to mess up the algebra with
Okay.
my multiplying it into minus one. But I see what you mean. So it's like it's what is it? It's n times or n plus one times sigma n plus one of f minus n times sigma n
Sigma
of
n.
f. Maybe.
Yeah. Yeah.
It, um, I hope I got the algebra right. Um, uh,
Is that fruitful at all?
um, this was so the I think is a little is makes it a little problematic. So I guess it's fruitful, right? If you know,
Mm,
sorry,
the rate.
yeah, exactly. So you need to start knowing some rates, right?
Hmm. Okay.
And so that and like we saw
Yeah.
last
Okay.
time
That makes sense.
that was fruitful, right? We like what like that was exactly what we did when we considered like C alpha functions. That knowing C alpha ness allowed us to get some type of rate for the convergence of sigma n. Um,
Yeah. Okay.
and then you're right. Like see like we're we're getting somewhere. You can get somewhere with this type of observation. I bet you could do some version of what we did last time. I bet you could get to with this identity.
Okay.
So yeah, imagine this might be useful. Sorry. Okay. Yeah, that's a nice observation. Thanks for pointing that out. Um, okay, so what's going on here? As we know, this looks like a strong result, right? We took these averages, and then we get this um, nice convergence result. And we discussed a little bit. We said how this was uh, well, this is convolution with so f sigma n of f was convolution with the Fair kernel, right? So it's fn involved with f, and this is the Fair kernel. Um, and f hat of n we saw was given by this triangle on the Fourier side. Um, Whereas the Dirichlet kernels was was just this function which was equal to 1 on minus n to n, and then 0 otherwise. So then we argued, okay, we could view this as some manifestation of like smoothing out on the Fourier side led to better decay, better estimates on the in terms of the functions themselves. Let me rephrase it. Let me phrase this like in just a more in a somewhat technical way. So if we have a sequence, let me go back, save this. So given a sequence, AK of complex numbers, say, you can define their partial sums, right, of the sequence, the sum from k equals 0 to n of AK, just the partial sums of the AKs, and then you can associate to such a sum as well the Cesaro means. So you could do this averaging for any sequence in any the partial sums of any infinite series. So the Cesaro means are given by sigma n is equal to 1 over n, which is sum from n equals 0 to n minus 1 of Sn, of the Sns. So and we did this with, of course, with the partial Fourier sums. But let me just emphasize that this is that a couple of points which are going to flesh out in your homework, and we're going to discuss more in office hours, is that so observation, one thing you can prove is that if this sum is finite, converges, then so i.e. what that means is that this sequence of partial sums converges as a sequence to S, then sigma n converges to S as well. So if the series is summable, then it's also Cesaro summable. But the converse is not true. So there are more sequences which are Cesaro summable than are summable. So converse not true. And as a means of an example, so an example, take the sequence AK is equal to minus 1 to the K. So then what are the SNs, the partial sums of this sequence, are either given by, well, this is 1 minus 1 plus 1 minus 1, etc. It's equal to 1 if K is odd, I guess, and 0 if K is even, right? So this as a series, so this means that AK does not converge, right? So this is not a convergent series. However, if we look at the Cesaro means of this sequence, however, if I look at sigma n of this series, this is 1 over n times the fraction, or times S0 plus Sn minus 1, which are always equal to 1/2, right? Is that right? I think these get 1/2. I should make sure I'm doing this right.
I think it's 1/2 at like even n or something like this. But if you have an odd n, then you have like one more one than 0, so you have like
okay, so it converges to 1/2, right?
yeah, it's like 1/2 plus O of 1 over n.
Yeah. Sorry, so they're not equal to 1/2. Yeah. This converges to 1/2 as n goes to infinity. Yeah, right. If I have it's 1/2 for even n, and then 1/2 plus a little bit plus a little 1 over n as n goes to infinity. Okay, so this converges to 1/2. So that this sequence is Cesaro summable. And it kind of, what it does is kind of picks out the average of these two guys, of 1 and 0. So this is kind of what's going on. It should be this should tell us that it's easier to prove. It should be easier to prove, as we did, like that the Cesaro means of a function converge back to a function than it is to just consider the Fourier sums by themselves. And we can look at we can also look at alternative methods of summation and see what they bring us. So alternative methods of summation. In particular, there's one due to Abel. So Abel summation, Abel means, and summation. And this, in fact, predates Cesaro. Cesaro means. And what's here? So the definition is that if I take a sequence of complex numbers, we say are Abel summable to S if for every R strictly less than 1, the quantity A of R is equal to the sum from K equals 0 to infinity of A, K, R to the K converges, and so these 2 points have to be true, and the limit as R goes to 1 of A of R exists and is equal to S. Right, so your Abel summable, if these are called the Abel sums of the AKs. If these converge, and moreover, if they have if I look at the for each R, I examine the sum for each R strictly less than 1, and then if I look at this family of this function of R that I get at the end and take its limit as R goes to 1. If this has a limit, then I say we're Abel summable. And this is even, it's, so you can, again, check, like, if you're summable, then you're Abel summable. But in fact, as you'll do in your homework, this is even a weaker requirement than Cesaro summable. So, so an observation is that if AK is Cesaro summable, then it is Abel summable. So everything that's Cesaro summable is also Abel summable. But the converse is not true. So converse, not true. Sequence 1 minus 2 plus 3 minus 4 plus 5, etc. This is equal to the sum from 0 to infinity of minus 1 to the k equals 0 to infinity of times k plus 1. and you can check that this is Abel summable. In fact, A of R is equal to, so from k equals 0 to infinity minus 1 to the k plus 1 r to the k. This is equal to the function 1 over 1 plus r squared, r to the r squared. Which converges to 1/4 as r goes to 1. Okay. But then this is not, you can try and verify that this is not Cesaro summable. But this is not Cesaro summable. Okay, so we can also, the point here is we can consider the Abel sums of Abel Fourier sums. So given, what we'll do, so we'll fully answer question from first class, or from week 1, I think it was the second class, about the Dirichlet problem in the disk. Unit disk D. So how will we do this? Well, given f, a function f on the circle, whose Fourier series is given by the sum from n equals minus infinity to infinity of f hat of n e to the I in theta. You can associate to this, so this is the Fourier series. You can associate to this the Abel sums, Abel means. A R f of theta are defined to be the sums from n equals minus infinity to infinity of r to the absolute n times f hat n e to the I in theta. So for every r less than 1, so for every 0 less than or equal to r less than 1. And we can now ask, like, rather than ask whether this series is convergent, so whether the partial Fourier sums converge, we can ask whether the partial Abel sums converge for each r less than 1, and then try and take limit as r tends to 1 of take a limit as r tends to 1 at the end. Okay, so so and note, so that by inserting this power r to the n, as long as we can define the Fourier coefficients, this object is summable. Yeah, we have, in fact, uniform convergence for on each fixed ball of radius, r naught, where r naught's less than 1. So if f is integrable, f is Riemann integrable t, then ARF converges for every, this is convergent for every r less than 1. And you have, in fact, uniform convergence in theta, right? Because
Professor, why is that? I don't see.
Why is that? Because so let me prove it real quick. So A r f of theta is in absolute value, if I just throw absolute values inside. So let's fix an r. Fix an r less than 1. Then this is less than or equal to the sum from n equals minus infinity of f hat n. If I put absolute values around e to the in theta, I just get 1, right? And then I just have r to the n. But if f is integrable, the f hat n's are bounded. They're uniformly bounded, right? This is just some integral of f. Right? So it's bounded by some, this is bounded by some constant. The constant depends on f, of course. But so I'm left with, so this is less than or equal to this sum. It's a geometric series, right?
Professor Lowry,
Yeah.
is this just because our choice of r now that's just because our r is less than 1?
Strictly less than 1.
Yeah. Okay. Cool.
Because r is strictly less than 1, that this is summable.
So we really needed both integrability and our choice of r is really important here.
Yes. Yeah. And so then you see, okay, well, this converges for each r less than 1. But now that but it's a delicate matter now if I want to let r tend to 1, right? So that's it's not immediately clear, right? Because this, just putting absolute values inside is not going to tell me much about the limit, in particular because I can't just take a limit as r tends to 1 here, right? If I let r equals 1 here, I get a divergent series. So there is something to say now about taking the limit as r tends to 1. And let's try to understand that limit and try and understand when we can take it. So okay, so the next observation is that AR F as a function of theta can be written as convolution with the kernel, is F convolve with a function P sub R of theta. And how do I see this? Where PR theta, this is called the Poisson kernel, is given by the sum from n equals minus infinity to infinity of r to the n, absolute n, e to the I n theta. This is called the Poisson kernel. Okay, so how do we see this? Well, we're just gonna it's the same argument as sussing out the Dirichlet kernel, the Lefebvre kernel. So this is the sum from n equals minus infinity to infinity of r to the n f hat n e to the I n theta, which is equal to the sum from n equals minus infinity to infinity r to the n 1 over 2 pi minus pi to pi f of phi, let's call this e to the minus I in phi, phi, e to the I in theta, which is equal to the integral. I can can interchange the integral in sum because I have uniform convergence of the series for each fixed r, and so I get 1 over 2 pi times the integral from minus pi to pi of f of phi, the sum from n equals minus infinity to infinity of r to the n e to the I in theta minus phi, phi. So there I see I have this is PR of theta minus phi. So when I have the Abel means are given by convolution with a kernel. All right, so if you believe me that it's sort of easier, Abel summation is sort of the weakest requirement, and now we have a kernel appearing. What's our guess? Is this a good one or a bad one? Where the index, it's a little bit different, the question, because the index is now R, and we're interested in the behavior as R tends to 1. Right? There are no issues with anything R. So the big question about summability is what happens when R tends to 1. So the behavior of this kernel that we're interested in is just like before when we had a discrete indices for our kernel. Now we have a continuous one. Well, it's a parameter R tending to 1. But we want to know the limiting behavior of this object because R tends to 1. So this is a family of kernels. And what's the guess?
My guess is yes, it's good.
Yeah.
It's gonna why, but that's my.
Well, one reason, I'm taking a class reason is that like we wouldn't bring up another bad one probably. So we're already stuck with the Dirichlet kernel, which is a bad kernel. So that's a silly reason. It's just I think a little bit of intuition was just this observation that it was sort of easier to have a series be Abel summable than it was Cesaro summable. So I should expect the convergence properties here to be even better than the convergence properties for Cesaro sums. And the Cesaro sums produced the Fair kernel, which was a good kernel. So I'll expect this one to be good as well. And that is the case. So we can prove a lemma about the Poisson kernel. So lemma, if then PR of theta is, we can in fact find a nice formula for it. An alternative formula for it is 1 minus r squared divided by 1 minus 2r cosine theta plus r squared. And part of this lemma is that PR theta is an approximate identity. And since described in class, it's a good family. Kernels. And the appropriate limiting behavior is R tends to 1. Right, there's a subtle difference. You can alternatively define a family of kernels with a continuous index instead of a discrete index, and there's no difference in the definition, or in practice.
Question.
Okay. Sorry. Yes.
So does that mean when you're describing the Fourier series, like with respect to the Poisson kernel, that you have to take the limiting behavior as R goes to 1 and n goes to infinity, or can you kind of abstract away the?
Yeah. There are two limits, right? So it's a little bit subtle. So let me try to explain it. so we start with a function, right? And then we find its Fourier coefficients for each n. So we find these f hats n's. Then now fix any r less than 1, right? Then this, and then I associate to that r less than 1 this object. So this whole sum here, right? And now I'm claiming that we can let n go to infinity and here always, as long as f is a Riemann integrable function. This series always converges, just because we've stuck in this factor that gets really small in front, right? So we kind of dispense with the limiting behavior as n goes to infinity at the outset, and then now the what we're left with is asking the behavior as r tends to 1, because we want to formally take r tends to 1 to recover the Fourier series back again, right? So so we're first taking a limit as n goes to infinity and considering this sum, and then we're going to take a limit as r tends to 1. So there's a specific order here in the limits, and you're right. It looks a little funny, but we're relying really on the fact that series converges uniformly for each fixed r less than 1. Okay, so let's go through the proof of the lemma. Well, the proof of the formula is pretty similar to proving the various formulas we had for the Dirichlet and Fayard kernels. So PR of theta is equal to the sum r to the n e to the I in theta. And if I can break it into two pieces. So this is the sum from n equals 0 to infinity of omega to the n plus the n sum from n equals 1 to infinity of omega bar n, where omega is equal to r to the n, r times e to the I theta. And the series, one sums up to 1 over 1 minus omega. The other one sums up to omega bar over 1 minus omega bar. And then if I do some algebra, I'm not going to do the algebra in front of you. So I'm just going to copy from my notes. But I promise you get 1 minus omega squared divided by 1 minus omega squared. So I'm just going to add those two fractions together, and I claim I get this. And if I look back at what omega is, this is exactly equal to 1 minus r squared divided by 1 minus 2r cosine theta plus r squared. Okay. All right, so that's the formula for PR of theta. Now I want to kernels. So I need to verify three things. One, that it integrates to 1. 2, that if I put absolute values in the inside, I still get something that's bounded uniformly in R, right? As R, it's bounded uniformly independently of R. And then the third is that if I cut away a ball near the origin of thetas and look outside this ball, the integrals converge to 0. So I'm going to prove a little formula for the denominator. So note, I'm going to prove an estimate for the formula for the denominator. 1 minus 2r cosine theta plus r squared. This is equal to 1 minus r squared. So I need to, I subtracted 2r, and now I need to add back 2r again. So plus 2r times 1 minus cosine of theta. And this is always positive, right? Because cosine theta is always, this is always non-negative rather, right? So this tells me now that the Poisson kernel is always positive. In this, it'll suffice to verify the first and third aspects of being a good kernel. Right. On the other hand, if I take R sufficiently close to 1, say, let's take R bigger than a half, and if I move away from the origin, so if I pick theta, absolute theta, be bigger than delta and less than pi for some fixed delta, for any fixed delta, then this denominator, 1 minus 2r cosine theta plus r squared, is bigger than or equal to a fixed constant, c delta bigger than 0. Just because I've and that follows just because I've bounded cosine away from 1. I made sure cosine is a little bit smaller than 1 by a fixed amount, and then I just have this nice one here and this positive r squared here. So okay. So what? Yeah, or even looking at this formula here, I have something. This might be 0, but for here, I have as long as r is bigger than a half, this thing is strictly positive, right? This is bigger than some fixed constant. If cosine is bounded away from 1, cosine of theta is bounded away from 1, and then I'm bounded by a fixed constant below. So there's the proof, and this means that PR of theta is less than or equal to 1 minus r squared over this c delta if delta is less than or equal to theta is less than or equal to pi. And r is bigger than a half, say. And this implies property 3 of the approximate identity definition. Right, because as r tends to 1, this thing goes to 0. Right, so the integral is going to go to 0. Okay, and then for for properties 1 and 2, PR of theta is bigger than or equal to 0, so I just need to check 1. And then I can integrate term by term. This is equal to 1 for every r. And I can, again, term by term integrate. So for this first property, you want to go back up to this definition. I only get something. I have to integrate each of these eti and thetas, and I only get something when n is equal to 0. And so then I'm just left with 1. Right. Okay. So PR thetas are a good kernel, and the theorem we get, this lemma implies the theorem if f is continuous function on the circle, or even if f is just Riemann integrable, then ARF go like this. As r tends to 1. So I have uniform convergence function f. Okay, any questions about this? This theorem again follows from what we proved about being a good kernel.
Sorry, a clarification. So the Poisson kernel is not a good kernel unless R tends to 1.
So being a good kernel is or a good family of kernels is a limiting property, right? It's some properties involving like uniformity of some estimates in this case in R. R is the parameter. It's a family of kernels parameterized by R, strictly less than 1. And the interesting thing about being an approximate identity, right, is if you recover back the function, if you convolve with the kernel, do you recover the function back again as you let the parameter tend to the endpoint? Before we were letting the kernels were indexed by a discrete parameter by n. So before kn approximate identity indexed by n and z and natural numbers, say, and we saw that kn convolve with f as n goes to infinity. So the theorem we proved about being an approximate identity was that it's an approximate identity because as I let n go to infinity, it acts as the identity under convolution, right? For convolution. Here for these for the Poisson kernel, so is an approximate identity. And indexed by R less than the parameter ranges from 0 to 1, and the relevant limiting behavior is the limit as R tends to 1. Just like up here, the relevant limiting behavior was as n tends to infinity. Now the limiting behavior is R tending to 1. Limit of interest, the limit, sorry. For these PRs. Does that make sense? Does that make sense?
Yes. Yeah, thank you so much.
Yeah, so we just need to be a little flexible with our definition now of family of kernels and what we allow the index of the kernel of the family to be. And you can go back through the definition and try to and just verify for yourself that nothing changes really, and the theorem doesn't change if I have a continuous index as well. Okay, so what can we do with this theorem? The claim is that now we can understand the Dirichlet problem. So recall the Dirichlet problem. On the disk, which is all z in the complex plane, say, such that absolute z is less than 1, or it should be strictly less than 1, say. And the boundary of the disk is the unit circle, which we're calling T, is all z and c such that this is equal to 1. So we're trying to solve the Dirichlet problem, the problem D, where we're trying to find a function u such that the Laplacian of u is equal to 0 on D, and I restrict u to the boundary of the disk, so to T. This is equal to some function f. So here f is given. F, say, is a function continuous function, say on t, is given, and the goal is to find u. Okay, so we're trying to solve this PDE, and here Laplacian. So we can think of u is equal to u of r and theta, and Laplacian is equal to I wanted to put minus or plus. So dr squared plus r plus 1 over r squared d theta squared. So this is the Laplacian in polar coordinates on the disk. These are polar coordinates. Okay, so we're trying to solve this problem. And at the beginning of class, we saw that the candidate for a solution is u of r theta is equal to the sum from m equals minus infinity to infinity of f hat m r to the absolute m e to the im theta. So if you scroll back through your notes, we wrote down this as a candidate function for u. And the point now is we immediately recognize, just from the previous slide of the notes, that this is precisely the Poisson kernel convolved with f, convolved with the boundary data. So this is called the boundary data. We have a given function on the boundary of the disk, and we're trying to find the function u inside has Laplacian equal to 0 and equals f on the boundary in some sense. So this equals is we have to make sense of a bit what this means. But now we have a way of making sense, right? This i.e., so this is our candidate, u of r and theta is none other than PR convolved with f of theta. So it's nothing but the Poisson kernel convolved with f, evaluated at theta. So this is pretty neat. And the theorem we can prove right. Okay, so let me just say one thing. So that we're going to prove a theorem in a second, but or maybe I'll say the theorem and then I'll discuss it a little bit. So if f is just say continuous on t, in fact, if it's just integral on t, you can still make sense of this. Then if we set set u of r theta to be this, then u is C2. So the function u is in fact smoother than f, and then we can make sense of its Laplacian. So Laplacian of u is equal to 0, in fact. So this solves the Dirichlet problem, at least in the sense that we found the u part. Now we need to worry about our boundary data. B is that u has the right boundary behavior. So if f is C0t, then the limit as r goes to 1 of is equal to f of theta. This is uniform in theta if f is a continuous function. If f wasn't continuous, and we still have this limit existing pointwise. And C, we'd have this limit existing at points of continuity, rather. Sorry. And C is there was a question about this about uniqueness stuff at the beginning of class, but C is, in fact, we have uniqueness. This is the unique solution. If F is continuous on T, then U of R theta is the unique solution to the Dirichlet problem. So we can give a full answer to this question in partial differential equations. We can solve the Dirichlet problem on the disk for continuous boundary data. In that we have existed, we can prove there exists a solution. In fact, it agrees with the boundary data in appropriate sense. Well, in this sense, we have agreement. If I take a limit, I converge uniformly to the boundary data, and moreover, I have uniqueness. This is the unique solution. So this is a real theorem. Okay, so any questions about the statement? And let me just say one more thing. Like, not only that, we have a form. This is a formula for the solution, right? We just you give me the boundary data, and then the solution is given by just convolution with its kernel. So this is an explicit formula for the solution in terms of the boundary data, because we saw that PR is a function that we could write down. We wrote down in the previous slides. So this is a formula for the solution. Any questions about the statement of the theorem? But please stop me if questions arise. Okay, so what's the proof? Well, we kind of did part A already. So part A, so this is a series. There's a series representation of the solution. And if I fix any row less than 1, then I have inside R less than row less than 1, I can differentiate term by term. Because the series, once I fix a radius row, then I have uniform convergence inside the ball in terms of R and the ball of radius row and the closed ball of radius row, right? As long as row is less than 1. So then I can differentiate term by term, and we saw in the beginning of class that this formally solves the equation, right? That we built this series from solutions to the equation by separating variables. But what this tells me is this means that U is C2. But in fact, it's a series, right? In R and theta. These are nice. These are nice smooth functions, right? R to the m, absolute m, and e to the im theta. Those are smooth functions. So in fact, the solution is C infinity. So in fact, U is C infinity. And Laplacian of U equals 0 can be checked by explicit computation, explicit calculation. So you can verify that. It's an exercise. B, this follows from this, the boundary behavior follows from what we just proved. Yes, sorry.
So you said U is C infinity, and that's on the disk, or the disk only and not the boundary?
Yeah, right. On the boundary, you might just be a continuous, no better than continuous. Part B tells us that that in this sense, U is equal to F on the boundary, right? Right. U tends to, if I fix a theta and let R tend to 1, I recover the function F.
Right.
So what you should think about is like the boundary might be very, I might have a very rough function on the boundary.
Right.
F might be a rough function. But inside, if I solve the problem inside and I just look at
Still
inside,
be C infinity on the inside.
on the inside, yeah. So this is a
Weird.
yeah. So this is a kind of fascinating and deep fact about PDEs. And what should come to mind a little bit is if you've taken 112, like the complex analysis, that once you have one, that once you have one derivative, then
Like conformal maps can be
if you have a whole an analytic functions are infinitely differentiable functions. Once you have one continuous derivative, then you have infinitely many. But okay, it does turn out though that also and this is like a two-dimensional thing. So you might think, okay, there's something complex analysis going on. These are precisely called in fact, these are called harmonic functions on the disk. So there is something complex analysis going on here. But it turns out that this smoothing property happens even in higher dimensions as well. You can still solve this problem in the three-dimensional ball, for example. And the code word is that this is in fact a feature of solutions to this type of PDE. And the code word is called elliptic regularity. This is something called an elliptic PDE, and it turns out that like once you have a solution, then there's magic happening. And even if you initially find your solution in a class, say you look for a C1 solution or something, once you know it solves the equation in an appropriate sense, then you can in fact a posteriori prove that the solution that you found is smooth. Even if you start off with say with something not so great on the boundary of on the boundary, if your boundary data is not so great. So this is something called like a elliptic regularity, and in parabolic equations, like the heat equation, something similar happens. If you have some very rough distribution of heat, and you turn on a switch and let time evolve, immediately the distribution of heat becomes a smooth analytic function, C infinity function. So there's some deep stuff going on, and like I think you're absolutely right to like raise your eyebrows at the conclusion of the theorem, right? You start off with rough F, and then all of a sudden it gets nice and smooth inside. It's a really deep fact, and like a bit to be honest, like a bit mysterious as well, in that people are still trying to prove if I have, so not all PDEs look this pretty. If I still have some semblances of ellipticity, whatever that means, then do I still have smoothness? There's still like active research in this area. So like you very quickly get into some deep waters that I'm not really an expert in, but I suffered through some of these things in graduate school, so I still have some scars that will never leave me. Yeah. Okay, so okay, part B. What was part B? Part B was that I recover back the functioning and the boundary. Well, we proved this already. This was the content of the theorem I stated on the previous page, that the Poisson kernels are an approximate identity, and so I have this uniform convergence as R tends to 1. So part B is done. Is an approximate identity. So it's a good kernel. And for part C, now I have unique. Now I want to know uniqueness. I want to know this formula I wrote down that this is the only possible solution, given a continuous function f. There's only one solution to this equation. And here, well, this is proving uniqueness theorems can be. This can be quite hard. But here we have a clue about how to start. One, we have this nice Fourier-like representation of the solution, and we know we already proved a uniqueness theorem for Fourier series. So the idea to prove uniqueness is let's take any other solution to this equation, satisfying A and B. So let me, maybe I should be more careful about how I phrase this theorem. So if I have uniqueness in that A and B are satisfied, or let me write this on the next page. What I mean by uniqueness. So if I have any other solution in the sense of A and B, then it has to be the solution U. So uniqueness. So assume f is C0 T, and suppose V of R theta satisfies so the Laplacian of V is equal to 0, and the limit as R tends to 1 of V of R theta is equal to F of theta uniformly. Suppose these two things satisfy. I want to show that V of R theta is equal to U of R theta. That these are the same function.
Quick question on that.
Yeah.
Would it be sufficient to show that they're equal, like as R tends to 1 or something, or just that they're literally equal?
I want to show that they're equal for each R less than 1. In fact, yeah. So yeah. So yeah. The tricky thing is R is strictly less than 1. I know I'm assuming that they have sort of the same limiting behavior as R tends to 1, that they both recover F again. So that I'm going to try and bank on that to prove the theorem.
Oh, right, because that's in the assumption.
Yeah, exactly. So let's so if I fix, how do I do this? I'm going to try and show that these functions have the same Fourier coefficients. So I fix R such that 0 is less than R is less than 1. Then V of R theta, if I freeze R, then I view this just as a function of theta, then this has a Fourier series, right? Has a Fourier series. Without saying anything about convergence of Fourier series, I'm just going to try and find its Fourier series, right? The Fourier series given by sum from n equals minus infinity to infinity, v hat of Rn e to the in theta. And where v hat of Rn are the Fourier coefficients, remember R is fixed, 1 over 2 pi minus pi to pi. V of R theta e to the I n theta, e to the minus I n theta, d theta. Okay, so now let's try and find, I realize my V's and R's are looking very similar. Let's find these Fourier coefficients. So now I'm going to try and use that V solves the equation, right? So Laplacian of V equals 0 means that I claim that this means that each Fourier coefficient solves the ODE v hat prime prime of Rn plus 1 over R v hat prime Rn minus n squared over R squared v hat Rn is equal to 0. All right, and these primes are supposed to refer to the R derivatives of this function. So for each fixed R, I can associate its Fourier series, the Fourier coefficients. But then for each fixed n, I have a function of R, right, as well. V hat of Rn is a function of R and n, right? And for each fixed n, it's just a function of R. And I claim that this implies this for each Fourier coefficient. And that just follows by taking derivatives of this formula and using the fact that finding using the equation that V solves. So I want to take R and theta derivatives. So let me just explain a little bit one of the formulas. So for example, how to get this, if I integrate by parts, d squared v if I look at the Fourier coefficient associated to d squared d theta squared of v, this is equal to, I claim this is equal to minus n squared v hat of Rn by integration by parts. I just integrate by parts this formula in theta, and I recover this, and that's how I arrive at this. That's how I arrive at this equation. Okay, so I'm not going to do the details of that, but I will say that I will try and write down the solutions to this equation. This is just an ODE now for each fixed n. So therefore, v hat of Rn is equal to some coefficients an times r to the n plus bn times r to the minus n. We saw this ODE in the second day of class already. For some constants a and b, an and bn, but if n is bigger than or equal to 0, I want so v is bounded implies that v hat of Rn is bounded, right? So v is a C2 function, right? So its Fourier coefficients are bounded. So that means I can't have, this means that bn should be 0. Maybe I put n strictly bigger than 0 here. And if n is less than 0, the same logic implies that an's are equal to 0, right? Because I want b to be a bounded function. Sorry, I'm not sure why there's an absolute in there. Okay. So so how do we find an's? Well, I use my other ingredient that I know about v, namely I know its limit as r tends to 1. So I just let r tend to 1, and this will imply that an is equal to 1 over 2 pi minus pi to pi f of theta e to the minus I n theta d theta. So this is equal to f hat of n. right? Okay. So this means that the Fourier series are the same. So v of r theta and u of r theta have same Fourier series, which implies that u for every r less than 1, which implies that u equals v by the uniqueness theorem. For Fourier series. So if I know if two functions have the same Fourier coefficients, whether independently of asking about convergence, right? If I have two functions with the same Fourier coefficients, then they have to be equal as long as they're continuous functions. Okay. Did that make sense? I realize I went a little quickly in the proof. Does anyone have any questions at the moment, or you're welcome if they don't, if it was too quick to even have a question, please let me know later if you're looking over it.
I'm just wondering if there's a better way to do this than to, I think, essentially solve it again, solve the entire equation again.
The uniqueness proof?
Yeah, like, okay, so you started with taking some other v that solves it, and my guess as what was going to happen is you would like consider v minus u. Which, so v minus u is 0 on the boundary, and it's also harmonic. I thought maybe you'd be able to get forward with that. Is there something like that?
Yeah. So yeah, v equals 0 is v minus u is 0 on the boundary, also harmonic, and then now you want to use a uniqueness theorem for harmonic functions, right? Yeah. So like there is a complex analysis proof to this. There are a couple different proofs of this theorem.
Oh, okay.
Like that. Understandably, I gave a Fourier series one in class. But yeah, there, like, especially if we're in the disk, right? Like this, then there are a couple different proofs, and like exactly what you said should work if you rely on some things about harmonic functions.
Okay.
Yeah. Good instincts. And like you could definitely see why I chose this proof too. For class, this is a very we've kind of we've worked to be able to use this uniqueness theorem for Fourier series, and with like your argument as well, you need to work to show some things about harmonic functions, as well. So there's like trade-offs to each approach, I guess. Okay, so I think I'm going to stop right here. We're also almost out of time, and this is a kind of a natural place to stop. Next time, we're going to discuss Hilbert spaces and what's called the L2 convergence in Fourier series. And we're going to start getting close to our like motivations for measure theory. I'm not going to start measure theory right away, though, because there are a couple other things. Once we study Hilbert spaces a little bit, start discussing Hilbert spaces, there'll be a couple other convergence results for Fourier series that'll be within reach. So we'll take a couple weeks to do those. Christina, if you're here, I think your presentation is probably going to be on Thursday, given how far we got today, next week instead of Tuesday.
Okay, cool.
All right. Thanks, Christina. Any other questions before we go?
Just a quick question, just about the presentations. I saw last night that today's for office hours is open, so I put my name down. So I'm happy to take a stab at that. But I can also do a later one if you'd like.
Sorry, is I for some reason thought it was filled already, but maybe it's switched. But yeah, Andy, go ahead, please. If it's open, then go ahead. Let me just.
No, already. I mean, I don't want to take it.
No. If there is, so there was a name before, but maybe so like a deleted name. So right now I see. Okay. There. Um. All right. Let's see. So there was some confusion about which was number 6 and which was number 7. And I know I thought Bryn wanted to do the presentation to switch to one next week. She'd emailed me about it. So Annie, do you mind coming? And if Bryn, I'll give, if there is some confusion about which number she put her name down for, I'll give her priority for the one this week. If not, do you want to do it?
Sure.
Okay. So just come in 5 minutes to office hours, and that'd be great. If you're ready to go.
Will do.
Okay. And then I'll be adding more of these topics pretty soon. I'll probably next week I'm gonna add a bunch more topics. Most of them are going to be about measure theory, I think. So for now, and then we'll come back to Fourier analysis again towards the end of the class. So there'll be more Fourier analysis topics later too. Okay.
Professor, I wanted to ask about discontinuous functions.
Yeah.
I guess we're going to talk about this later, I assume, but I guess what happens with those? Because is uniqueness still true? I guess my mental picture is that uniqueness would still be true even if convergence doesn't apply at the points of continuity.
So that's a true statement. But then uniqueness fails, though. I mean, and you can kind of see this by just changing around the function at a couple points, right? Just changing changing a function at say 1 point, you can see that uniqueness fails at points of discontinuity because they can kind of be chosen randomly, right?
Right. So even if the function was defined on the entire disk, like you could still have uniqueness fail at the limit on the boundary, even if they're identical.
Okay. So for this PDE theorem that we
for the PDE.
Yeah. So you need to assume it's.
Or would there be like a degree of freedom that's like left because for every point of discontinuity there's like a degree of freedom or something kind of thing?
Yeah, it's. So our proof definitely doesn't quite work if we're not assuming continuity all around the boundary, on the whole boundary, because we kind of relied on we really relied on continuity everywhere, I think, in the proof. I think I'm sorry. Let me try to think about this.
Because I can't really picture how like a solution, there could be two solutions that are identical on the inside, but then differ in the limit at a certain point. I don't mentally picture that, so I could.
Yeah. So if we take two functions,
assuming they both have a finite limit.
Yeah, I think so okay. I don't think we quite used the full strength of the continuity everywhere, right? So if we could still show that so I guess guess we would just get our proof. I guess would just get that the like u and v would agree on the individual ray. If we fix a theta at which the boundary is at which the f is continuous in the boundary, then we would have u and v agreeing on that whole ray. But I guess we wouldn't be able to say anything via our proof about thetas for which we had something bad about f in the boundary. If f was bad at a particular theta, I don't think we'd be able to say anything about that ray.
I see. Okay.
So the convergence wouldn't be uniform anymore in theta, right?
Yeah. Yeah, we wouldn't have uniform convergence in theta. Yeah. Yeah. So we're asking like if we had yes. So in particular the notion of uniqueness that we wrote down would be different. Like it doesn't apply, right?
Right.
Yeah, so these uniqueness questions get delicate as you assume less about. They're often contingent on the regularity of something, and they get quite delicate as you alter assumptions on the data.
Okay. Okay. Well, that's all.
You have to kind of ask even in what sense you're looking for what sense what sense the solution makes sense and stuff like that.
Yeah. Okay, that's it. Thank you.
Yeah.
Thank you.
Thanks, guys. I'll have office hours right now, so see whoever wants to come.